Hello everybody, today we are going to study the step-by-step process of instruction execution inside the CPU with the help of microprogramming technique. In order to understand microprogramming technique and concepts, it is essential to understand how the instruction execution is divided into sequence of micro instructions inside the CPU. Therefore, a revision of earlier topics on components of digital computer, how CPU works was felt essential and therefore is discussed next. A digital computer consists of input devices like keyboard, mouse and output devices like monitor, printer and main cabinet unit consisting of CPU, memory and I/O controllers. The main cabinet unit contains the connectors and ports for connecting various input output devices. Whether the computer is a small palm top, laptop, desktop, the central component of the cabinet unit is a single chip microprocessor called CPU. Powerful computers like mainframe or a supercomputer often contain multiple central processing units. These machines are used to perform parallel operations so as to serve thousands of concurrent multiple users at the same time or perform a complex computation in less time. All the mobiles, whether a low cost mobile or a costly smartphone, contains a microprocessor which is a single chip CPU containing computing as well as signal processing capability. The user enters the input using input devices. The information is stored in the main memory. The CPU processes the information in the memory by executing the program placed in the memory. A program is a sequence of instructions written to accomplish a particular task. The processor executes the sequence of instructions one by one to complete the execution of the program and produces the desired result as the output of the program. The results produced by the CPU are stored in the memory. These results are then shown to the user with the help of output devices like monitor. The computer functioning is completely controlled by the program under execution, except the interruption by the operator or input output devices. The objective of today's topic is to understand how the CPU works with microprogramming, how an instruction is divided into a number of instructions placed in the micro memory of the CPU and is then executed. Before we understand how CPU works, it is essential to understand the architecture of the CPU and its main components. The architecture and the components vary from one CPU to another and from one manufacturer to another. Therefore, there are common components in every CPU which are necessary to perform computation and are necessary to understand the working of the CPU. There are 8 common components in every CPU, which are: first, arithmetic and logical unit called ALU in short. Second is floating point unit, which is called FPU in short. Third is control unit, which is called CU in short. Fourth is prefetch unit. Fifth is decode unit. Sixth is internal cache. Seventh is registers and eighth is bus interface unit. These components and their logical interconnection help us to understand the working of CPU. However, looking at the physical structure of the CPU, it looks like a single chip with large number of pins connecting the system buses and the mechanism for dissipating heat with fins and coolants. The above components are integrated with the help of millions of transistors inside the chip. The arithmetic and logical unit, called ALU in short, is used for arithmetic and logical operations. The arithmetic operations like addition, subtraction, multiplication and division are performed by the ALU. The operands required for these operations are given to ALU either from internal registers or memory locations. The results are also stored in internal registers. The Boolean operations like AND, or NOT comes under logical operation. For example, if an AND operation is applied between two numbers expressed as binary 1110 and 0001, the result of the bit by bit AND operation is 0000. Similarly, if the OR operation is applied between the two binary numbers 1110 and 0001, the result of the bit by bit OR operation is 1111. These operations are also used to compare numbers and find out if given numbers are equal, greater or less. The arithmetic operations involving decimal numbers or floating point numbers are performed by floating point unit called FPU in short. Most CPUs today have multiple ALUs and FPUs that work concurrently to perform various arithmetic operations on floating point numbers. The second important component is control unit, which coordinates and controls the various operations and activities taking place within the CPU. For example, in order for the ALU to perform arithmetic operations on two numbers, the first step is to transfer the input operands from registers to the input of ALU. The second step is to perform computation. The third step is to transfer the outputs of the ALU and store the result into one of the specified registers. The control unit ensures that the second step starts only after the completion of first step and so on. In short, the control unit ensures the strict sequence and timing of various operations taking place inside the ALU, FPU and various other units of the CPU. The data transfer between CPU and memory are also controlled by the control unit through the timing signals. The control unit derives the timing signal from an external unit called system clock. In order to better understand control unit and microprogramming, it is essential to understand the internal sequence of the operations taking place for execution of an instruction. The execution of an instruction inside a CPU is divided into a sequence of steps. Each step is executed with a micro operation. Micro operations are functional or atomic operations of a processor. The execution of all the instructions inside the CPU can be described with the set of micro operations. Many of these micro operations are common among the instructions. Some of these common micro operations are: first, fetch cycle; second, interrupt cycle; third, fetch operand cycle. Now, let us start with a fetch cycle and the associated micro operations in it. The fetch cycle occurs at the beginning of each instruction cycle and fetches instructions from the memory. 4 registers are involved in the fetch cycle. First register is memory address register, called MAR in short. This register is connected to the address bus and specifies the memory address for a read or write operation. Second is a memory buffer register, which is called MBR in short. The MBR, a memory buffer register, is connected to the data bus. In a write operation, it contains the last word returned to the memory from the CPU. In a read operation, it contains the last word read from the memory. The third important register which is involved in the fetch cycle is a program counter register, called PC in short. The program counter holds the next instruction to be executed. Fourth register involved is the instruction register, which is called IR in short. It holds the last instruction fetched. At the beginning of the fetch cycle, an address of the next instruction to be executed is placed in the program counter. The first micro operation is moving that program counter value to memory address register. because this is the only register connected to the address lines of the system bus or address bus in short. The second micro operation is to bring the instruction from the main memory to CPU. This involves placing MAR on the address bus and activating read signal of the control bus. Next, the instruction for the memory comes on the data bus. The data which is interpreted as an instruction because program counter value was sent on the address bus is placed on the data bus and then copied to memory buffer register. The program counter register is then incremented in a manner so as to point to the next instruction. Also, the MBR contents are then copied to IR. Thus, the simple fetch cycle consists of 3 steps and 4 micro operations. Each micro operation requires data movement from one register to another, and if the data movement of the micro operation are independent of each other, they can be performed in a single step, else separate steps are needed. So, one of the important objective is to divide the fetch cycle into sequence of steps, where the next step is dependent upon the previous step, and each step involves few independent micro operations. Once the instruction is fetched, the next step is to fetch the source operands if at all they are required for execution of the instruction. The operands, if available in CPU in the form of registers, can be directly used by the instruction. However, if the operands are available in the memory, the address of the data to be fetched must be brought to the memory address register. The address may be directly available with the instruction or may be indirectly made available to memory address register through one of the registers. In short, the fetch operand cycle includes the following micro operations. First step is transfer the address of the operand to memory address register and activate read control signal. Second, the data placed on the data bus by memory after access time t of the memory. Third step is data is copied to MBR and then is available for the instruction to use. The next cycle is the interrupt cycle. We have discussed the fetch cycle and fetch operand cycle so far, and the next cycle is the interrupt cycle. At the end of every instruction completion, all the interrupt signals are checked. If any of the interrupt signal is enabled by the external device, the interrupt cycle occurs, else the next instruction in the sequence is executed. The nature of the interrupt cycle varies from one machine to another. In general, in the first step, the contents of the program counter are stored on the stack through the following steps. Transfer the program counter to the memory buffer register. Next, transfer the stack pointer to the memory address register. Assign program counter a new value as defined in the CPU hardware, and then transfer the MBR contents to memory through write enable signal in the control signals, so that the program counter value can be saved on the stack. Most microprocessors provide multiple types and or multiple levels of interrupts. Therefore, it may take one or more steps to obtain the address where the contents of program counter must be saved and get the new value of program counter from the hardware defined address or indirectly from a predefined memory location. All the above operations may be represented by a single micro operation. So, an interrupt cycle may be represented by a sequence of multiple micro operations. The sequence and the type of the micro operations vary from one microprocessor to another microprocessor. The next cycle is execute cycle. The fetch and fetch operand cycles are simple and predictable, and they are common across all the instructions. Each of the cycle involves a small fixed sequence of micro operations, and the same set of micro operations are repeated each time. The same is not true for execute cycle. For a machine with n different opcodes, there are n different sequences of micro operations that can occur. That means, for the execute cycle is different for every instruction which is available in the CPU. First, consider a simple instruction like add. The format of the add as specified is add R1 comma in brackets R4. Generally, in bracket means address of R4 is to be used, and if it is add R1 comma R4, that means the register R1 is one of the operands in the add, but R4 is not one of the operands. The address specified by the operand, the address where R4 is pointing to, that memory location contents are brought, and those memory location contents are added to R1 to generate the result back in R1. The instruction implies that add the contents of register R1 to the contents of the memory location pointed to by the register R4. The first step is to copy the contents of the register R4 to MAR. The second step is for the memory to put the contents on the data bus as pointed by the R4. The third step is to copy the data to memory buffer register, and the fourth step is to add the contents of R1 to the contents of MBR. The instruction cycle consists of fetch, fetch operand and execute cycle. The fetch and fetch operand cycles are broken into predefined fixed number of steps and involves micro operation. For execute cycle, as we have seen in this add, different sequence of micro operations exist for each instruction which is available in the instruction set of the CPU. In short, we can say that the behavior of the functioning of the processor can be decomposed into elementary operations called micro operations. Knowing precisely the requirement of these micro operations, the control unit of the central processing unit must be designed in a manner so as to help execute the above micro operations in the desired sequence, so as to achieve the execution of the instruction with the desired result, keeping the data dependence and the sequence in mind. Now, let us recall the contents of the CPU. The CPU consists of ALU, registers, internal data paths, external data bus and control unit. The ALU performs arithmetic and logical operations. The registers are used as internal memory locations of the CPU and are used as operands for most of the arithmetic and logical operations. Some registers contain the status information needed to manage the sequencing of the instruction. The example is program status word is one of the register. The contents of the program status word registers are checked and the sequencing of the instruction is decided based on the contents of program status word. Another component is internal data bus, which are used to move the contents from one register to another or from one register to ALU or from ALU to register. The external data paths link registers to memory or IO modules by means of system bus. The control unit coordinates and controls the sequencing of various micro operations taking place in the CPU. The execution of the program consists of the operations involving these processor elements. As we have seen, these operations consist of sequence of micro operations. A careful analysis of micro operations reveal that all the micro operations fall into one of the following categories. First category is transfer data from one register to another, transfer data from register to external interface, transfer data from external interface to register, perform an arithmetic or logical operation using registers as operands, or producing result in one of the registers. Looking at the above micro operations, we conclude that the control unit performs two basic tasks. first important task is sequencing. The control unit controls the sequence of the micro operations to be executed one after the another based on data dependence issues and as per the requirement of the instruction to be executed. Second important task of the control unit is execution. The control unit helps and coordinates the execution of every instruction which is executed in the CPU. In general, the control unit operations along with its input and output can be described as below. The input to the control unit are clock. The clock unit helps to execute one micro operations or a set of independent micro operations within one clock cycle. Second is instruction register. The opcode of the current instruction is used to determine which micro operations to perform in the next execute cycle. Third is flags. These are needed by the control unit to determine the status of the processor and the outcome of the previous arithmetic and logical operations. Fourth is the control signals from the control bus. The control bus of the system bus provides signals to the control unit. So, in short, we have studied that there are 4 inputs to the control unit and the outputs of the control unit are the control signals which are generated by the control unit within the processor. These are of 2 types, those that cause the data to be moved from one register to another. Another are those that activate specific ALU functions. Second output of the control unit is control signals to the control bus. Again, these are also of 2 types, control signals to the memory and control signals to the I/O modules. So, to summarize, what we have studied today is that one of the important components of any computing platform, whether it is laptop, palm top, tablet, desktop, mainframe or supercomputer, contains a central processing unit called CPU in short. The CPU is also called single chip microprocessor. We have studied the various components of the CPU and how these components are connected together to execute an instruction. The most important unit as we have studied is the control unit. We have learned how the control unit performs the sequencing of micro operations which in turn leads to the execution of the instruction. Also, we have studied how an instruction is divided into micro operations and how these micro operations are implemented with the help of control unit.